Okay, here in this video we're going to analyze what's called a summing amplifier. So here's our op amp. Again, the non-inverting input is grounded just like it was in the inverting amplifier case. We got a feedback resistance, and this time we have multiple inputs instead of just one input like with the inverting amp. And you can see I labeled these inputs V1, V2, and Vn. So there's three inputs here, but in theory you could have as many inputs as you wanted. So that's why I put an N here. So we're doing a 3-input case, but the same approach would be used no matter how many inputs you have. So it is important to realize that the summing amplifier, at least this type of summing amplifier, is a type of inverting amplifier because it's just what we had with the inverting amplifier case, just with multiple inputs. So we're going to come up with an expression for V out in terms of these inputs. And the way we're going to do that is by doing a node voltage expression here at node A, just like we did in the inverting amplifier case. So you can see I have these three currents, I1, I2, and IN, all flowing into this node. Okay, because this is node, this is all node A here. Having a little trouble with the pen, as you can see. Okay, but all this is node A. So all these currents I've defined except for little I are flowing into the node. And again, because of the virtual short that we talked about last video, this current into the op amp ideally is 0, as well as the voltage that's across the inputs. Okay, remember that's what we referred to as a virtual short. Alright, so if I do my KCL at node A, okay, so all these currents I have flowing in, the one flowing out, like we said, is equal to 0, so I could write my KCL as I1 plus I2 plus IN, and then I'm just going to put IF on the other side of the equal sign, so it's minus IF. And then I write each one of these currents in terms of voltage using Ohm's law. So I1, now just like in the inverting amplifier case, because the non-inverting input is grounded, and remember we have 0 volts at ground, and because VI, the voltage across the inputs of the op amp, is also ideally 0, which means that voltage is the same on both sides. So the non-inverting input is grounded, there's 0 volts across the inputs, which means the inverting input is also grounded, and that's where node A is. So just like before with the inverting amplifier case, in this case VA is equal to ground, it's equal to 0 volts. So now when I write I1, I1 is V1 minus VA, which is 0, so it's just going to be V1 over R1, right, since VA is 0. And then I2 will be V2 minus 0 over R2. Okay, IN will be VN over RN. Okay, and then IF is V0 minus VA, which is 0 over RF. Alright, so now if we just go ahead and solve for V0, you can see that V0 is going to be minus, and then we have RF over R1 times V1. Then we've got, added to that, we've got RF over R2 times V2, and then RF over Rn times Vn. Alright, so you see what you end up with is that V out is the weighted sum of inputs. See, each input is weighted by the feedback resistor divided by the resistance at that input. And then there's a minus sign out front, which again indicates inversion. In fact, the reason why this input where we put the minus sign is called the inverting input is because anytime you have an op amp where the non-inverting input is grounded, V out will be 180 degrees out of phase with your inputs. Okay, so whatever this weighted sum comes out to be, if it comes out to be some positive number, well, V out will be the negative of that positive number, so it would be 180 degrees out of phase with whatever this sum is. Likewise, if this sum came out negative, then V out would be positive because double negative, as you know. Okay, so you'll see other examples of op-amp circuits where this again happens, where the non-inverting is input, and again you'll see there's an inversion between the output and inputs, or input if there's a single input. Alright, well, this is why it's called a summing amplifier, because the output is equal to a weighted sum. Now, if you made all these resistors the same, so that the ratios were all 1, then you would just have an output that was the addition of all the inputs. And again, it'd be inverted.